Okay, so let's first complete classical today, and then maybe we'll decide it at the very end. Okay, so we'll first take slipping motion ka case once again, and then we will take fluid dynamics. And if you want me to take anything else, you can tell. Okay, chalo, get started. Let's get started, people. Okay. So please give heading slipping motion or rotational motion with slipping cases, basically. Let me just remove this and reapply this. Okay. Yes. So we are running rigid body dynamics, people. And in this, we are learning the slipping cases. So let's recall first of all what is the rolling motion very quickly. Okay. So rolling basically means two things are happening simultaneously, like we know. One is rotational and other is translation. Okay. So we can have any object which is capable to roll. Remember, we have taken a question in class, like whatever questions we took in the class were related to solid sphere, and I have told you the replica of the thing can be created for hollow sphere, for solid cylinder, for hollow cylinder, for disc, for ring. Any object which is capable to roll, people, same question can be created for all of them. What is the first important thing that will change in all of them? That is the moment of inertia. Depending upon moment of inertia, all the other data will also change, people. Okay, so whatever questions that we learned, remember that we learned for solid sphere, but same exactly can be created for any other object too. So maybe what we can do today is we'll take a problem on hollow sphere, but just a different variety, but the procedure will remain the same, nothing else. Okay. Anyway, so it has a center of mass. It is moving in the forward direction with velocity of center of mass, and if it also rotates with some angular velocity omega, so two things are happening simultaneously, rolling and rotation and translation, and together you call it rolling. We know that. Anyway, so for rotation motion, yes, pardon.
Sir, can we take the question that I sent you on your email ID and Insta as well? And you thought that you said me that the question is quite good.
Yes, we can, but again, I will. But it includes spring motion too. But okay, let's see. First, let's complete this revision part, and maybe then we can take that question.
Yes,
Okay.
sir. Yes, sir.
Sure. Okay. But okay. But yes. Like I'm yet to. No worries. Chalo. Let's first discuss this. So what do we have? For rotational motion, people, we have got this thing, which is v velocity at any point along a tangent that is given by v is r omega. So here we have got vcm is r omega, and here we have got also we have got vcm, not vcm is r omega. Just a minute, I just got lost for a while. I'm thinking something now. Okay, okay. So for when any object, when it rotates, people, the tangential velocity is given by r omega. You know that. So at this point, we have got a tangential velocity r omega. Here also we have got a tangential velocity r omega. Okay. Here also we have got a tangential velocity r omega. But if you take a point here, people, let's take a point here. Now this point is going to rotate along this circle, people, along this part of the circle. Correct? It has got a smaller circle. It has got a smaller radius. So here it has got small r omega. Here it has got small r omega. Here it has got small r omega. Basically, as you go towards the center, what happens? The value of r decreases, and at center, r becomes 0. At center, there is no tangential velocity. At center, r omega does not exist, people, because r becomes 0. So that additional component becomes 0 at the center. Okay? However, at all the other points, you have got r omega. Along with r omega, you also have vcm, because all of them are moving in the forward direction. Tell me one thing, when the object rolls, all the objects are moving in the forward direction with a velocity of r omega, with the velocity of vcm. So even this has got vcm because all are moving in the forward direction. Even this has got vcm. Okay. Even this point has got vcm. Even this point has got vcm. All the points have got a forward velocity of vcm and there is r omega velocity, which is the tangential velocity. So we can take different cases here. We have got one case here where there is a forward velocity of VCM. There is another forward velocity of r omega. So what is the total velocity, people, at this point A? I can say that the total velocity at this point A is VCM plus r omega. Okay. Similarly, here at this point, okay, we have got r omega, and here we have got VCM. So what is the net speed at point B? I can say VB vector. Now there are two velocities. One is VCM along I cap, and another is r omega along j cap, minus j cap, because it's in the downward direction. Here they were in the same direction, so you added them directly, people, because they were in the same direction. So magnitude will be added directly. Here the magnitude cannot be added directly now, because one is along x-axis, another is along negative y-axis, people. So minus j cap. Okay. So in that case, the magnitude of VB, the speed at VB, that will be under root of x square plus y square. No? So under root of VCM square plus r omega square. I hope you are with me. Similarly, we have got a point C. Okay. And we have got here again, all the objects are moving in the forward direction with velocity VCM, plus there is a tangential velocity, rotational velocity, r omega, which is going in this direction. So at point P or point C, whatever, usually we write this as point P. Why P? P stands for point of contact, P. So we are not going to use notation C. Let's use notation P. That stands for point of contact. So here we have got two cases. Either VCM is greater than r omega, okay, or r omega is greater than VCM, or both of them are equal. So VP will be magnitude of mod of VCM minus r omega, depending upon who is greater. And now this is the factor which decides. This is the factor which decides which kind of slipping we are going to have, forward, backward, or no. So now let's learn the cases. So first, obviously, you already know what happens when it comes to no slipping case. In no slipping case, the point of contact is at instantaneous rest. VP is basically 0. And what happens? VCM minus r omega or r omega minus VCM, that is 0. Or basically, you can say VCM becomes equals to r omega. Simple. Again, since VCM is r omega, if you differentiate both the sides, people, derivative of rate of change of VCM with respect to time, this is radius is constant, derivative of omega with respect to time. This is what, people, acceleration of center of mass. This is r into what is this? D omega by dt, that is alpha, angular acceleration. So ACM is r alpha and VCM is r omega. You can also say the rate at which the linear velocity increases will be equal to the rate at which the angular velocity also increases. Because of which, you know what happens, people, because of this equation, what happens is, so somebody had also asked me in the chat box that, how are you keeping now? So, well, I'm keeping good, because as you can see now, my voice is loud enough and I'm able to do voice modulation. But I think if I'm going to speak more aloud, then I'm going to cup it out. But okay, it's okay. So, sore throat is good. But anyway, so VP, people, like we know, it is actually VCM minus r omega, but we know VP is 0. Now the question is, sir, will VP always remain 0? Sir, what if VCM increases? That's what we learned. Now, if VCM will increase, r omega increases by the same rate, people. Look at this, dVCM by dt, this is r into d omega by dt. So yes, VP will always remain 0 in this particular case. If VP is initially 0, then VP will have to remain 0. Why? Because if VCM increases, then r omega will also increase by equal rate. So suppose if initially this is 20 and this is 20, because of which VP is becoming 0. Now, if VCM increases, people, suppose this becomes 30, then r omega will also become 30. If suppose VCM decreases, suppose it becomes 10, then r omega will also become 10. But the point is, the rate of change of VCM will be equal to the rate of change of r omega, because of which VP will always remain 0. And this case is known as no slipping case. In no slipping, VCM is always r omega and ACM is always r alpha. Any questions? Anyone? Let's proceed. And you can tell me if you're writing too. You probably have written all of this earlier as well, but you can still tell me if you're writing anything. Okay? Chalo. Next. Now let's learn the first case of forward slipping. So that is basically when, when VCM is greater than r omega. Okay? Let's learn this. So we have got a forward velocity vcm, there is an angular velocity omega, and now at this point p, we have got, see, um, since vcm is greater than r omega, remember vcm was going in the forward direction, r omega is tangential, it's going in the backward direction. Huh? R omega is going in the backward direction. So the question is, where should be the net velocity? Forward, backward, what? So it depends who is greater. If VCM is greater, where will be the net velocity? It will be in the direction of VCM. है ना? So since VCM is greater than R omega, the velocity of VP is actually in the forward direction. So this is VCM. Here you have got omega. And now we have got VP, which is in the forward direction. First, I hope you understood why VP is in the forward direction. Because VCM is greater than R omega. Okay? Next. Next is, since basically what is going to happen is, people, the object which is going to roll, the point of contact now has a velocity with respect to the ground. So it is going to slide, it is going to skid. Okay, because of which, what is going to happen, if there is a moment, like suppose you have this object, if it is going to skid now like this, there will be a friction in the opposite direction. Simple. If this was at rest, then there will be no friction. But now if there will be some skidding that is going to happen, if there will be some slipping that is going to happen, because now slipping is happening, now the point of contact has velocity with respect to the ground. So now, since there will be some slipping in the forward direction, there will be friction in the backward direction, which will try to oppose this slipping, people. So first of all, this is known as forward slipping because it's going in the forward direction. It's going in the direction of VCM. Okay? So this is first of all known as forward slipping because it is going in the direction of VCM. Okay? Next. Now, friction has to oppose this slipping, obviously. So friction will act in the opposite direction. Okay. Now, people, VP was VC. Okay, wait. Let's not do it this way. Hang on. So, people, friction is a kind of force. Force means it will have acceleration too. The question is whether the acceleration given by this, is it going to accelerate something or decelerate something? So people, F is against VCM. F is in the opposite direction of VCM. So it is going to reduce VCM. Do you agree with this or not? I repeat, F is in the backward direction. So don't you think it will reduce the value of VCM now?
Yes, sir.
Okay, that's it. So what we will say is F will decrease VCM. That's important. Second, at the same time, F is also going to generate a torque now. Because here is the center, here you have got R cross F. And what is the direction of the torque? It's clockwise. R cross F, this is how you write, right? R cross F. Basically, just draw a clock, people. If suppose, listen, if R was here, if F was here, then R cross F is like this. Simple. Okay. If R is here and if F is here, okay, then R cross F is like this. Simple. You just have to draw a clock from A to B. Or we also know you keep fingers in the direction of R, curl it in the direction of F. Okay. How is the thumb going? Thumb is going inwards, but how's the fingers curling, people? Fingers are curling in the clockwise direction. R is downwards, F is on the left, and how are the fingers curling? Fingers are curling clockwise. Okay. Simple. So there is a torque now. Friction is going to generate a torque, and that torque is going to be clockwise. Don't you think it is going to support omega now? Because this torque is not opposite to omega. This torque is supporting the omega. Omega was going like this, people. And torque is supporting the omega. Remember, torque is nothing but what? Angular force. Tau is I alpha. Right? Tau is angular force. If torque is there, it means angular acceleration is there. Force, this friction will generate a torque. Since torque is there, it means angular acceleration is there. The question is this angular acceleration in the direction of omega or in the opposite direction of omega? Obviously, it is in the direction of omega. So this will increase the value of omega. This will now increase the value of omega. So I can simply say another thing here, and that is torque will increase omega. Clear? Now, Vp was people Vcm minus R omega initially because Vcm was greater than R omega. Na? So Vp was Vcm minus R omega. But now what is happening? Friction is decreasing Vcm. Yaar. So Vcm is going to decrease and torque is increasing omega. So omega is going to increase. Until when will this keep on happening? Suppose initially Vcm was 30. Let us say R omega was initially 15. Suppose, I'm just saying, suppose VCM was 30 and R omega was 15. Now VCM will decrease and omega will increase. So it will keep on happening because there is continuous acceleration. There is continuous retardation. Both is happening simultaneously here, people. This force is continuously going to retard VCM. So 30, 29, 28, 27, it is going to decrease and torque is continuously increasing omega. So 15, 16, 17, 18. So this will keep on happening like 29, this will become 16 because this one is decreasing, this one is increasing. 28, 17, 27, 16. This is going to keep on happening. And as soon as they will reach a common value, people, what will happen? Vp will become 0. As soon as Vp will become 0, what will happen? Friction will stop.
Friction stop.
If Vp is 0, object is at rest, like object is at not object, the point of contact. It is at the point of contact is at instantaneous rest. And as soon as the point of contact is at instantaneous rest, why will the friction? Friction will not stop exerting. If friction will not be there, torque will not be there, force will not be there, no acceleration, velocities will remain constant. Now you are back to no slipping case. I repeat. Once you reach 0 value, as soon as Vp becomes 0, simple, the point of contact is not skidding now. Since point of contact is not skidding, friction is not going to be applied. Friction does not exist after that. If friction will not exist, there is no deceleration, there is no torque, velocities will remain constant. Now you have reached a no slipping case. So forward slipping happens, but thanks to the friction that it brings back the thing to no slipping. Is this concept clear very much once again?
Yes, sir.
Good. Others, please ask me if you have any questions. Okay? Should I proceed? Okay? Chalo. Now let's learn the backward slipping case. Okay. So what do we have? We have got this ball. And now we have got VCM, now we have got omega. So at this point of contact P, what do we have in the forward direction? In the forward direction, now I have got, let us say, VCM. In the backward direction, I have got R omega. But this time, R omega will be greater than VCM. So whenever this happens, we call it backward slipping. Why? Because since R omega is greater than VCM, where is the net velocity? It will be in the direction of R omega. It will be in the direction of R omega. Okay. So here we have got omega. Here we have got VCM. And now net velocity Vp will be in this direction, which is actually equals to R omega minus VCM this time because R omega is greater. Now, since the slipping is happening in the backward direction, people, you call it backward slipping. But what will happen to friction? Friction will try to oppose the slipping. Friction will now act in the forward direction. It will oppose the slipping. Now, since force is in the forward direction, acceleration is in the forward direction, what will it do? It will increase VCM, don't you think this time? Force is in the forward direction, people. Acceleration is in the forward direction. Now, this time, VCM will increase. Also,
Yes,
there is a torque. Now, the direction of torque is R cross F. This is R, this is F. The direction of torque is R cross F. This is going anti-clockwise, people. This is going against omega. So since torque is there, alpha is there. Alpha means angular acceleration, but angular acceleration is opposite to omega. It means omega will be decreased. Omega will be decreased. So omega is decreasing this time. VCM is increasing this time. Again, until when this will keep on happening? Until when they will become equal. Same story. Suppose this was 30, this was 15, this is decreasing, this is increasing. Same story. 29, 16, 28, 17, 26, 18, and until they become equal, it will keep on happening. Once Vp becomes a zero, friction stops. If friction stops, no force, no torque, you are back to no slipping case. I hope the slipping cases are cleared. Okay? We can take some random questions on this now. So let's take we can create anything. I think we took solid sphere in the class, so maybe right now we can take any random stuff. Hollow sphere, maybe solid cylinder, hollow cylinder, anything is fine. Let's take solid cylinder. So anything random, doesn't matter. Okay. So let's say we have a cylinder like this, and it is rolling with angular velocity omega. It has a forward velocity VCM. Okay, let's say this is a roll basically right now. Okay, it's rolling. So again, what do we have? We have got this point of contact somewhere here, BP. This is point of contact. Okay, P. And we can take a case. Suppose they have given us, let's say that initially, omega was 0. Okay, initially omega is 0, and VCM is there. VCM is there. Okay,
it's a forward case.
Yes, so automatically what happens, people? Obviously it becomes forward. Why? Because Vp is what? VCM minus R omega, and VCM is greater than R omega. VCM is greater than R omega because omega is 0, no? So VCM is greater than 0. So since VCM is greater than R omega, you can simply say it is a forward slipping case. Yes. Now since it's a forward slipping case, obviously what will happen? This is going in the backward direction. Friction will act in the backward direction. Vp is acting in the forward direction. Vp is initially Vp is equals to VCM because R omega is 0. Initially. Okay, R omega is 0. Now friction will act in the backward direction. We can apply some equations of motion here. First, if you have any questions in this much, you can ask me right now. Vp is in the forward direction and it is equals to VCM because R omega is 0 and friction will act in the backward direction. Okay. Okay. First of all, before I proceed, what is the moment of inertia right now? Moment of inertia.
It's a solid cylinder, so
half mr square.
Half mr square. Right?
Yes, mr square by 2, because you need to understand which axis this is, people. See, this is a cylinder right now. Okay, this cylinder is nothing but compilation of many discs. And if this is the axis, so this is as good as you have got a disc, and this is the rotational axis of the disc, which is given by mr square by 2. This is moment of inertia, mr square by 2. Here also we can say this is nothing but mr square by 2. Okay, where you have got nothing but compilation of many discs. And this is the same axis, people, just that here I have drawn the cylinder vertically. In our case, I have drawn it horizontally, but this is the same axis you are talking about now. So it is compilation of many discs. So here moment of inertia is nothing but mr square by 2. First important stuff. If it would have been a hollow cylinder, then it's just mr square.
2 by 3.
No.
Cylinder tha main sphere ho gaya.
Okay. Sphere is 2 by 3 mr square, yes. But when it comes to hollow cylinder, it is just mr square. Okay. So next. So okay. So now I'm going to just draw the front view, because I tried to draw a 3D diagram here so that you get a feeling of what exactly is happening. Now I'm just going to draw a front view of this. Okay. So from the front, it will look like a disc only. Absolutely, you know. But this is a cylinder, remember? Okay. And here you have got omega. Moment of inertia of this cylinder is mr square by 2. And we have got initially Vp is going in the forward direction, which is initially equals to R omega. And now friction is acting in the backward direction. Okay. Remember, the system is moving in the forward direction. Okay. So mass into acceleration. But do we have any other force apart from friction? No. So there is only one force, friction, and that is in the opposite direction. So you will write minus F. So Ma is minus F. Correct? So I can say that. हाँ बोलो.
सर Vp equal to VCM होगा ना, क्योंकि ओमेगा तो 0.
Sorry. I wrote R omega. That's mistake. Absolutely. Pp was VCM initially and R omega was 0. So Vp was VCM. Yes, thank you. And there was friction in the backward direction, right? Now system is moving in the forward direction. So acceleration acts in the forward direction. But technically this is deceleration. We know that. But let's understand how exactly we do understand deceleration from the numerical perspective. Mass into acceleration, it is equals to sum of all the forces. So mass into acceleration. People, there is only one force, frictional force, which is acting in the opposite direction. So that's minus F. Okay. So you can say that A is minus F by M. This minus tells you that acceleration is actually decreasing acceleration or retardation, and that you already know that there will be retardation. Because this friction, when it comes to forward slipping, this has to retard VCM. We know that. This has to retard VCM. VCM will decrease. We know that. And it will also generate a torque. So now let's learn this from torque perspective. Any questions so far?
No, sir.
Good. Now let's learn this from torque perspective. So when it comes to torque, people, torque is I into alpha. Okay. Torque is, this is F, and what is the perpendicular distance from the axis of rotation? It's radius R. The perpendicular, because torque is what? It is force into perpendicular distance. Huh? Perpendicular distance from the axis of rotation, that's radius R only. Okay. So torque is F into capital R radius. Moment of inertia. See, in the class we took solid sphere, you wrote 2 by 5 mr square. Hollow cylinder, now it becomes mr square by 2. Likewise, you can create this question for all the other objects which are capable to roll. Okay, this is alpha. So Fr is mr square alpha by 2, and we already have that A is minus F by M. Okay, just a minute. Huh? So from here we are going to get alpha, people. So what is alpha? Fr, wait, R and square gets cancelled. So 2F upon Mr, this is alpha. We have got alpha. Alpha is 2F upon Mr. Now, people, V is U plus 80. V is U plus 80. So V is the final linear velocity. We don't know the value of that. What is the initial linear velocity? VCM. Hello? What is acceleration? Minus F by M into T. Don't you think this now makes sense? Because what happens as the time goes? If the time keeps on increasing, what happens to the velocity? It is decreasing. And that is what expected, because friction is continuously going to decrease the velocity. Now, as we see, friction is going to decrease the velocity. As the time goes ahead and ahead and ahead, the velocity will continuously decrease. Eventually, what will happen? The velocity will become zero. And somebody may, a good question here can be asked, find the time taken when the velocity will become zero. When, basically when VCM, yes, when VCM becomes zero. No, not VCM. So what exactly is this?
Sir, V.
Just V, but which V should we call it? VP.
So no slipping case. Start.
No, I'm not thinking that. This becomes linear velocity, no? But hang on. Or rather, okay, for no slipping, the VCM will be equals to R omega. Okay, let's just keep it right now this way. This is one example. T increases, V decreases. Okay. We have another example. Omega is omega naught plus alpha t. Like, very similarly to this kinematical equation, we have got another kinematical equation. Omega is omega naught plus alpha t. Now, omega naught was zero. There was no initial angular velocity that was given to you in the question here. There was no initial angular velocity. Where is it? Initially, omega is zero. Okay. Next, alpha you just found out. This 2f upon mr into t. So what happens to omega, people? Omega becomes 2ft upon mr. Omega becomes 2ft upon mr. Okay. And then what the case that we know is the no slipping case, where VCM becomes equals to R omega, people. Remember, this is actually the value of VCM after time t, because VCM is continuously decreasing. This is initial VCM. Let's call initial VCM as V naught maybe. Okay, I'm just going to say, I have written now that initially omega is zero. Let's say initially value of VCM is V naught or anything. Let's call it V naught. Add it if you want in the question, if you have copied this thing. Let us say initially omega is 0, and let us say initially VCM is V0. And VCM is going to decrease. We know that because friction is going to oppose VCM. I repeat, friction is going to oppose VCM, so VCM will decrease people. So that's what. So as we see, this is final value of VCM. And what is the initial value of VCM? It is V0.
Okay, sir.
Any confusion, please ask. Okay? VCM is decreasing, and is omega increasing? We had guessed that friction is going to decrease the VCM, and it will also it will generate a torque, and it will increase omega. Is omega increasing? Yes. Look at this. As time increases,
Yes, sir. It's
omega
increases with time.
Yes. So let's take the case when no slipping is reached. So when what happens at no slipping? VCM becomes equals to R omega. This happens at no slipping. Okay. So what is VCM? V0 minus F by N into T. And R omega. What is omega? 2FT upon MR. I hope you are with me. Tell me if not. We are taking the no slipping case. Okay. So what do we have? R gets cancelled. V0 is 2FT upon M plus FT upon M. We have found out 3FT upon M. This is V0. So we have got people 3V0. Sorry. We have got V0 is 3FT upon M, or I can say MV0 upon 3F. This is the time taken by the cylinder to reach the no slipping case. A very good question like this could be: find the time taken by the cylinder, because initially there was forward slipping. Now find the time taken by the cylinder to reach the no slipping case. Time taken is MV0 by 3F. And similar questions you can now create for hollow cylinder, for ring, for disc, for hollow sphere, solid sphere, etc. Clear, everyone?
Yes.
Ask me if you have any questions. Good. Next. Just a minute, I will just find something. So we can take an incline motion problem too, maybe. You need to tell me what are the kind of problems you need me to take. So
Yes,
slipping
sir. Please.
an incline motion. Chalo. Okay, let's take this. So let's say we have got an incline motion, and here we have got a sphere or a cylinder, or let's take ring this time, maybe, or disc. Okay, chalo, ring. Let's take a ring. Okay, so we know moment of inertia of this ring, that is mr square. It is capable to rule. Okay, and okay, let's say this is omega. We have got VCM. Now the thing is, there is a weight which is going to be initially wait, what I'm going to say right now is thinking something. Okay, okay. So we have got weight here in the downward direction, mg. Mg has got two components, horizontal and vertical. We know this is theta. This also becomes theta. This becomes mg cos theta. This becomes mg sin theta. People, mg sin theta is a force which is acting in the direction of VCM. Mg sin theta is a force. Okay, it is acting in the direction of VCM. It means VCM will increase. Now, how will mg sin theta contribute to omega, people?
No contribution.
Why?
It passes through the center of mass.
Perfect. Mg sin theta, people, it passes through the center of mass, because of which there is no torque. Because I hope you remember, torque is F into R perpendicular. So if this is R, if this is force, then torque is F into R. Here, torque is F into small r. F into small r. If people, F passes through center, R becomes 0. Here mg sin theta passes through passes through center. It does not contribute to any torque. So important thing to realize here is that mg sin theta does not generate any torque. Does not generate any torque because it passes through center. It passes through center. Okay. Since it does not generate any torque, it means tau is 0. Tau is 0. It means I alpha is 0. It means alpha is 0. It means there is no angular acceleration. It means omega is not affected, people. Omega is not affected. So tell me one thing. If suppose I would have given you initially, let's say this ball was at no slipping. Suppose initially it was rolling, purely rolling, and suddenly there is an incline or whatever. Okay? So Vp is supposed to be Vcm minus R omega. Initially Vcm and R omega were equal, because of which Vp was supposed initially 0. Okay, but now Vcm has increased. Because of mg sin theta, Vcm has increased, but R omega remains the same. So it's something like initially both were 20 and 20. Now because of mg sin theta, Vcm has increased, let's say 21, 22, 23. But what happens to this 20? This 20 remains the same. It means Vcm is going to be greater than R omega. We have got a forward slipping case. Okay. So whenever forward slipping is going to happen, friction will come to the rescue. So the object must be rough. Remember, people, that rolling motion is impossible in a frictionless surface if the object is initially at rest. I repeat, if the object is initially at rest, and if you are going to push it, then it is not going to roll if there is no friction. If the object is already spinning, and if you keep it on a frictionless surface, then it will keep on rolling forever. Okay. But if it is initially at rest, and then if you will push it, and if there is no friction, then it will never roll, people. Without friction, rolling is impossible, provided it was initially at rest, or initially at forward slipping, or initially at backward slipping. If initially it is already rolling and then you keep it on frictionless surface, then it will keep on rolling, people. Then that's fine. Okay. So forward slipping is going to happen now. Okay. So friction will act in the backward direction. Now it's just about our equations. So what do we have? We have got theta, we have got this, we have got mg sin theta, and this will be acceleration. And now friction is going to act in the backward direction. Here, F. So mass into acceleration, which is the force in the direction of acceleration, mg sin theta, which is the force in the opposite direction, friction, F, people. Let's say this is equation 1, or let's say acceleration is basically mg sin theta upon m minus F by m, or I can say acceleration is g sin theta minus F by m. Okay. So what happens to Vcm? V is u plus at. Let us say initially the value was V naught, people. Again, let us say initially the value was V naught. So V will be equals to Vcm after time t. Okay, after some time t, Vcm will be initially, let us say it was V naught, and finally it is A into the, what is A? A is g sin theta minus F by m into t. I hope you are with me. Okay. Next. Now, similarly, this friction is going to generate torque, but mg sin theta is not going to generate torque. Friction will generate torque. This is R cross F. It is going to generate torque in this direction. Okay. So what do we have? We have got tau, which is equals to I alpha. Okay. Tau is F into R once again. Perpendicular distance is again R, people. I, it is mr square this time into alpha. Okay. So we have got F, which is equals to mr alpha. F, which is mr alpha. Okay. Okay. I'm thinking something. Copy this. I'll just check something. So what exactly should we, try to derive here? That's what I'm thinking. Okay, okay. So friction is going to increase omega, people. It's clear. Have a look. R cross F. Friction will increase omega, but friction is also decreasing velocity because it is opposing acceleration. It is opposing the forward motion. This is the forward motion. Friction is opposing the velocity, and it is also increasing the omega. Basically, eventually, what will happen? Again, the no slipping case will be reached. We know that here. Have a look. Where is that? VCM is increased. R omega. Sorry, not this one. PP is VCM minus R omega. VCM is going to be decreased. What will friction do? Friction will also increase omega. So this will keep on happening again when VP becomes 0, and eventually no slipping case would be reached. And what happens at no slipping? At no slipping, I know that VCM becomes equals to R omega. I also know that A becomes equals to R alpha. I hope you remember ACM or A, whatever you want to write it. It becomes equals to R alpha. So people, can I directly write this as M into A then? I'm using the condition of no slipping. Remember,
Yes,
this happens at no slipping. No? So R alpha, I have written it as MA. Put this here. Put this here. Okay. So A is G sine theta minus F by M. Okay. So A is G sine theta minus MA by M. MM gets cancelled. So A is G sine theta minus A. So 2A is G sine theta. We have what acceleration is G by 2 sine theta. Now this is a kind of question which could be asked. Find the value of acceleration so that the no slipping case is reached. Now I think we took a very similar question in class for solid sphere, for which we had derived an answer of 2 by 7. Sorry, no, 5 by 7 G sine theta.
yes, sir.
Yes. Okay. So we have got that acceleration ka question too. But this is for ring now. So for ring, the acceleration value at no slipping is G sine theta by 2. Make note. So mostly the questions will revolve around this. And I think you probably know what you're supposed to do. Just apply VCM is R omega. Just apply A is R alpha for no slipping cases. You are comfortable with applying Newton's law. The only thing where you have to take care is to identify whether it's forward slipping or backward slipping, and the value of torque. Torque is supporting or opposing, and R alpha. The value of R you have to take care of, where you will have capital R, where you will have small r, where the R will be 0. If the force is passing through center, then there will be no torque. So just you have to take care of these little things. So let's take fluid, people. So I have just decided to take some good questions on fluid. Basically, we'll take directly questions on Bernoulli's, people. I hope you remember Bernoulli's principle. So it's basically conservation of energy law. And that was P plus half rho V square plus rho G H. This was constant. This is known as total energy conservation, which we had found out using Bernoulli's theorem. And each of this has a term, like has a name too. P is pressure, absolutely. This is also known as, I think, pressure energy per unit volume. Correct?
Yes, sir.
Right.
Yes, sir.
Yes, sir.
Pressure or pressure energy.
Per unit volume. Per unit volume.
Okay, both of them are meaning the same quantity.
Yes. Pressure energy per unit volume is also the same thing. Pressure energy per unit volume. Okay. See, I will give you a small idea that why this is logical. Hang on. Okay. So a very lame idea, but I think it should help you. Energy is nothing but a kind of work. Work, you know, is PV. P delta V, actually, I'm just telling you it's PV. Okay. So energy upon volume is pressure. Now, does this make sense? Pressure energy per unit volume is pressure. Okay.
Yes, sir.
So a lame idea, but it's better to understand it this way. Okay. And similarly, half rho V square, this is kinetic energy per unit volume. half rho v square. This is kinetic energy per unit volume. Because see people, kinetic energy is what? Half mv square, hai na yaar? So kinetic energy per unit volume, this is half into mass upon volume v square. What is mass upon volume? Density, half rho v square. Okay? And rho gh, this is potential energy per unit volume. Potential energy per unit volume. Because common sense, again, here mgh upon volume. What is potential energy? mgh. So if you calculate potential energy per unit volume, so this is mass upon volume gh, which is again rho gh. So basically this is conservation only, people. Look now, pressure energy, kinetic energy, potential energy per unit volume is always constant. You can throw volume on that side. Basically pressure energy plus kinetic energy plus total energy, plus potential energy is a constant. Make a note. Ask me if you have any questions. One question on Bernoulli's is expected, people.
Yes, sir.
Chalo, next. Proceeding ahead. So we have got p plus half rho v square plus rho gh is constant, and now, hang on. Okay, let's just take a question. I've shortlisted some really good questions. The thing is, I'm not able to find time to type the questions, but I'll just take it. See, you guys have been busy in learning. I have been also too busy lately in working for all of you, but okay, no complaints, doing happily. Okay, so this is a TIFR 2011 question. I like this question, so I will take this one first. So there is some kind of a tube they have given us. Okay, something like this maybe. And there is a space here, actually. Okay, so there is a space here. There is also space here, and another tube is connected. Basically, remember this is water. Huh? Like it's there is no white color available. Huh? Okay, but there is yellow color available. I think yellow can work as good as white. No, it doesn't work as good as white, but it's okay. So I'm just trying to create a space. So there is a small tube, an inlet or outlet, whatever you want to call it, is available here, and this connects directly to air. So outside we have got air basically, and we have got water. We have got water. Okay. They have given us that an ideal liquid is ideal. It has got density 1 gram per cc. See, I'm purposely taking all the units in CGS because you had also requested me, sir, I'm getting confusion. I'm confused in the unit conversion. So let's do the unit conversion stuff too. And they have given us it's flowing at a rate of 10 grams per second. So they have given us rate, people, 10 grams per second. What is the meaning of rate here, first of all? Can you tell me?
मतलब
Liquid is
एक
flowing at
सेकंड में वो 10
Flow.
ग्राम जा रहा है.
right. So how do you understand this? How do you understand this? So this is flow rate. They have mentioned us 10 gram per second. It is given to you. This is liquid flow rate right now. Simple. Look at the units, people. Gram per second. Gram means mass. Second is time. So this is dm by dt. Don't you think? Rate means what? Rate of change of something with respect to something. Na? Rate of change of mass with respect to time. You have to look at the unit. So dm by dt is given to us as 10 gram per second. I hope this is understood. Next. And they have given us that pressure at this position here is PA, and along the same horizontal level somewhere here the pressure is PB. Okay, and the radius. Just a second. E plus. The radius of this tube here, not the diameter, the radius of this tube, the small tube, is given to us. Let's say RA. The radius of this tube is 0.2 centimeter. This is radius, not diameter, okay? And the radius of this tube, the larger tube, RB, is 1 centimeter. This is 0.2 and this is 1. And they're asking us PB minus PA is the value of PB minus PA. I hope the question is understood first of all. Please tell me if you have any questions in the question. PB minus PA is being asked. See, many students first will think, sir, answer will be 0 because PA and PB are on same horizontal level. No, people, it will not be 0. The reason is, yes, they are on same horizontal level, but they are not in the same tube. In the same tube, the pressure would have been same, but they are not in the same tube. Okay? See, we have learned, suppose if I would give you, let's say, just one cylinder, then along any horizontal line, pressure will be same because they are right now in the same compartment. But if there are two different compartments, then the pressure will vary because there are different additional pressures. Right? Pressure along same horizontal line is same provided that you are in the same compartment. Here there is additional pressure of only this much, but here you have got an additional pressure of this much. This is P naught plus. I hope you remember how do you calculate the additional pressure? The
P naught plus H rho G.
Exactly. So this is water. If you want to calculate pressure here, then you have got air pressure plus additional H rho G. So that is different in both the cases. Okay. So you cannot say that the pressures are equal because these are different compartments. So never be tempted to write the answer 0 because the compartments are different. Okay. Now first let's learn dm by dt in detail. I hope you have copied the question. First quickly copy the question.
Yes, sir.
Okay.
सर RA का वैल्यू कितना है?
0.2 centimeter, 0.2 centimeter, and RB is 1 centimeter. Radius, huh? Sure. So we have got dm by dt, which is given by 10 gram per second. Okay. I can write this as d by dt of what is mass density into volume. Density will be constant. It's an ideal fluid. Ideal means incompressible also. I hope you remember that. Okay. Incompressible means density is constant. Okay. D by dt of volume. So this is rho. D by dt of what is volume? Volume is area into length. So this is rho. Area for that particular cross section. If you take it constant, this is dl by dt. Rate of change of length with respect to time. This is velocity. So when you say flow rate, when you talk about dm by dt of flow rate, which they have mentioned it is going to remain constant, it is rho a. You also write this as q. Q is basically flow rate. We have learned this in the class, but we are just recalling it nicely. This is dm by dt and which is given by rho a. And if you remember, we had learned law of conservation of mass, people. The rate of change of input mass will be equal to the rate of change of output mass. And I told you that in high school you have learned equation of continuity is A1 V1 is A2 V2. But technically it should be rho 1 A1 V1 will be equals to rho 2 A2 V2. If the density remains same, then the rho gets cancelled. But who told you that density will always remain same? Yes, in our case right now, rho will be same. Why? Because it's an ideal fluid. But if it was not an ideal fluid, if the density changes, then rho 1 A1 V1 will be equals to rho 2 A2 V2. Otherwise, you will say A1 V1 is A2 V2 if the rho is same. Okay. So amount of input rate will be equal to amount of output rate, which is law of conservation of mass, people. The amount of mass input is amount of mass output. Any questions?
Yes, sir.
Okay. So they have given us Q. Q is rho A V. So I can find V from here, which is Q upon rho A. So this will be Q upon rho into pi r square. So let's find velocity in the first tube, in the first compartment. Q they have given us, which is how much? The flow rate, it's 10 grams per second. 10 grams per second. Rho, they have given us 1 gram per centimeter cube. Pi into r square. What is the radius of the first compartment? The radius of the first compartment is 0.2. I hope you are with me. Ask me if not. Remember,
Yes,
everything is in CGS right now. In exam, there are two options. Either you solve everything in SI or you solve everything in CGS. But at the end of the day, you need to remember that if you solve everything in CGS, if in a final question they are asking you to write the answer in SI, then you have to reconvert it. So it's always your call. whether you want to solve it in SI or whether you want to solve it in CGS. So right now, since everything is in CGS, I will keep everything in CGS. Now, why should I convert unnecessarily everything right now? Okay. So this is 10. Gram gets cancelled. Okay. Then I have got centimeter cube pi. Sorry, 10 upon 1 into gram gets cancelled. Actually, I'm just thinking I want to explain you the meaning of units also here. So I have got second inverse basically 1 centimeter cube inverse pi 0.2 square, that's 0.04, and this is centimeter. Wait, how exactly should I explain this? Okay, I'm going to write CC as centimeter cube. That's better. I'm going to write CC as centimeter cube. This is better. Okay. So gram and gram gets cancelled. 10 second inverse upon 1 centimeter raised to minus 3 pi 0.2 square, that's 0.04 centimeter square. Okay. So we have got 10 second inverse upon pi into 0.4. What do we have? Centimeter raised to minus 1. Okay. So people, centimeter raised to minus 1 goes above, that becomes centimeter. Second raised to minus 1, that goes below, that becomes second. I hope you understood the units. Don't you think this is a
Yes,
logical
sir.
unit? Because what is CGS unit of velocity? Centimeter per second.
Centimeter per second.
Okay. So just explaining you that how the unit things also work here. You don't need to, by the way, substitute the units. But the point is, if you will keep everything in CGS, automatically answer will be also in CGS. That's what I wanted to explain. But you don't need to write these units in the exam. You can ignore. But the point is, answer will remain in CGS. Okay. Okay. So what is the calculation of this? 0.04. Let's calculate. So we have got
79.62.
Okay, 10 divided by pi divided by 0.04. Yes, 79.57 centimeter per second. Chalo. So this is velocity in the first case. Let's similarly calculate velocity in the second case. That will be q upon rho pi r2 square. Q upon rho pi r2 square. Okay. Q flow rate, that's constant, people. Amount of input is equals to amount of output. So that's 10 upon rho, which is 1 pi r. Radius in the second case. What is the radius in the second compartment? That is 1 centimeter. Okay, this is an easy calculation. So this is just 10 by pi. So velocity will be massively reduced. This is just 10 divided by pi. 3.18. Okay, so this is 3.18 centimeter per second. Don't you think this is again logical that the velocity will be massively reduced? Initially, if the pipe is people thinner, you know how fast the water can move. If the pipe will be thicker, velocity will be very slow, which is very much logical. That initially the velocity, as we see here, was 79.57 centimeter per second. Now the velocity is reduced to 3.18 centimeter per second. Okay. Next, so we can apply Bernoulli's theorem. PA, like, or P1, whatever, P plus rho GH plus half rho V square. You know? This should be equals to P plus rho GH plus half rho V square of the second case. P plus rho GH plus half rho V square of the second case. Now listen. First case is PA. Rho GH, which is this H, important to recall. People, this is not the depth. Huh? This was potential energy per unit volume. This is the height from the ground. Write it in a note that rho GH in Bernoulli's theorem, when you write rho GH in Bernoulli's theorem, this is not depth, this is potential energy per unit volume, this is height from the ground. Okay. So you take wherever you want to take, you can take ground, but don't you think height of the first case and height of the second case is same?
Yes, sir.
A common mistake that students may do here is they will think that rho GH is this and rho GH is this. It's not this rho GH, because right now the meaning of rho GH here is potential energy per unit volume. Please take care of that. Okay? So height of the PA and PB is same. You can just cancel rho GH on both sides. Write it clearly. Ask me if you have questions. Okay? So PA plus half rho in the first V1 square rho V1 square. This is PB plus half rho V2 square. I think now we have got the answer. Now they wanted us to calculate PB minus PA. Okay, so half rho V1 square minus half rho V2 square. This is PB minus PA. So we have got half rho, we can take common, V1 square minus V2 square. This is PB minus PA. So we have got PB minus PA is equal to half is 0.5, rho is 1 gram per cc, V1 square, it is 79.57 square minus V2 square, which is 3.18 square. So this answer will be equal to 0.5 into bracket 79.57 square minus 3.18 square. I'm getting roughly 3160 people. Okay. Yes, it's absolutely correct. Outstanding. 3161 is the answer they have given us here. Nice. Okay. Acha, what will be the unit here? Now that's important. Let's learn something about units.
It will be CGS, no?
What's the CGS unit? That's a question.
Bar?
No.
Dyne per centimeter square.
Yes. It is dyne per centimeter square. Just a minute, actually. Dyne per centimeter square, because pressure is force upon area. Actually, copy this. So I just have, running nose, and it doesn't look good in the live screen if I'm, continuously pulling it off using handkerchief. So, okay. So what do we have? PB minus PA, which is 3160. Pressure is force upon area. Force is Newton, but in CJS it is dyne. And the area is meter square. In CJS it is centimeter square. Listen now, people. In exam, if you get confused in again CGS, if you don't recall, just remember the most fundamental formula. Derive. Right now, why do you need to guess that it is bar or it is this? Take a deep breath. Remember the fundamental formula of pressure. Force upon area. You know Newton. You know it will be dyne. You know area, which is meter square. You know it will become centimeter square. Just take a deep breath and recall. Okay. And what is one dyne? Now this is something you need to know in terms of SI people. What is 1 Newton in dyne?
1 Newton to 10 raised to power 5 dynes.
That's it. So 1 dyne would be 10 raised to minus 5 newtons. Okay. And 1 meter is 100 centimeter, and 1 meter square would be 10 raised to 4 centimeter square. So 1 centimeter square would be 10 raised to minus 4 meter square. So this is 3160 into 10 raised to minus 1 Newton per meter square. So this is 316 Newton per meter square. And what is Newton per meter square? This is SI unit, but SI unit has a name. What is that name?
Pascal.
Pascal. So this is 316 pascals. Okay. Similarly, if you mention bar, bar is actually 10 raised to 5 Newton per meter square. Right? So bar is 10 raised to 5 pascals.
Okay, sir.
Atmosphere, that was 1.013 into 10 raised to 5 Newton per meter square or Pascal, or you can say 1 atmosphere is 1.013 bar. Okay, now the irritation has started because I have been speaking too loud. Need to drink water. Just a minute. Okay. So next, let's take another question. Here we go. So here's another, just an interestingly good question. A very small one, but nice one. So they have given us a pipe. This was a question in IISc ka paper. Okay, and there is a pump here. And this height is h. They have given us here the pressure is p. They have given us here the pressure is p plus delta p. They have given us here the velocity is u. They have given us that density is rho and it's constant. And they're asking us the value of delta p, and then there are 4 options. So, okay, so what do we have? We want to find the value of delta p here. So we can apply Bernoulli's theorem. P plus half rho v square plus rho g h. This is equals to P plus half rho v square plus rho g h. This is in first case, this is in second case. Okay. So in the first case, pressure they have given us it's P. Half rho v square. Rho is rho, V is V1. Okay. Plus rho g h. This is potential energy. Remember, this is potential energy. Rho g, what is height, people? Capital H. I hope you are with me. Tell me if not. Any questions until here? Okay. Now,
No, sir.
I'm saying that the velocity here is v1. We don't know the value of v1. We don't know the value of v1. I've just said that the velocity is v1. This is equal to pressure in the second case. They have given us P plus delta. Have a look. Plus half rho. Velocity they have given us u square. Okay. Plus now this is potential energy. This is along the ground. So this is 0. Any questions, anyone?
No, sir.
Right now? Good. Okay. P and P gets cancelled. Okay. What is the relationship between V1 and U? Can you tell me? V1 and U, what is the relationship?
We can use that equation of continuity here.
Perfect. Okay. So rho 1 A1 V1 will be equals to rho 2 A2 V2. Density is constant. People, it's the same pipe. Radius is constant. Area is constant. So velocity will be same.
Okay, that was easy.
That's it. Velocity will be same. So half rho V1 square, half rho U square will get cancelled because V1 and V2 is same. It means V1 is also equals to U people. They both will get cancelled. That's it. Rho GH is delta. Simple. Make a note. That's the answer. Actually, there are options like minus rho GH. There are options where they have done 2 rho GH2 or something like that. So we just had to take care of the conventions and everything that we have got here. But this is the correct answer. Nice. Let me see what else. Okay, so there was a very interesting question that I saw on upthrust problem, people. A 2 liquid problem. First, I will make you recall 1 liquid problem, and then I will teach you this 2 liquid problems. Shall done? Next, okay. So, see, if you recall, we had done questions like this where I have given you suppose a sphere, and if I tell you that this is floating, but this is completely submerged. Floating but completely submerged. The diagram doesn't make sense. Wait, now it will make sense. This is floating but completely submerged. Then how do we understand this? We have got weight mg in the downward direction. If it is floating, it is total downward will be equal to total upward. So it has to be equal to the upthrust Ft. Mg has to be equal to the upthrust Ft. Okay, so Mg, what is upthrust? It is basically the mass of the liquid displaced. Upthrust is mass or weight, not mass. Mass is wrong word. Weight of the liquid displaced. Weight of the liquid displaced. Okay. So weight is basically mass into gravity. Okay. Mass is density into volume into gravity. But what is density of the liquid? It is actually sigma. Usually we use a notation sigma for liquid. Okay. Sigma. Volume. What is the volume of the liquid that will be displaced? It will be equal to the solid. Obviously, if you will put a mobile phone into the water, the amount of volume that will be displaced, that will be equal to a mobile phone. If you will just take a bottle and if you put it inside the beaker, the amount of liquid that will be displaced, that will be equal to the volume of the bottle. So whatever is the object, if you have a block, then what is the volume of the liquid that will be displaced? Equal to the volume of the block. So since I have got sphere, what is the volume of the liquid that will be displaced? It will be equal to the volume of the sphere, people. So mass is density into volume of the sphere. density of liquid but volume of sphere. I hope you remember this now. Huh? Mass is density of liquid into volume of sphere into gravity. Any questions in this? Do you recall this, people?
Yes, sir.
Yes, sir.
Please ask me if you have any questions. Okay. So this is sigma liquid, okay, into volume of sphere into gravity. And this is mass into gravity of what? Mass into gravity of sphere, people. So that's density of sphere into, then we have got volume of sphere. Mass is density into volume, no? Into gravity. This is density of liquid into volume of sphere into gravity. Okay. So that's fine. When this happens when the things are completely submerged, and then we have case partial submerged, we have case different cases that we had learned. But I am just making you recall this because I want to take a specific problem where two liquids, mixture of liquids are present actually. First to please copy this. This was a case where it is completely submerged. If it is partially submerged, then you know what happens now. I will
Yes,
also
sir.
just take that case.
That would mean that उतना ही volume का upthrust होगा.
That's it. So the volume of the liquid that will be displaced, that will be reduced now. That's it.
Yes,
So it
sir.
won't be volume. It won't be volume of sphere in that case. It will be volume of the sphere inside the liquid in that case.
तो सर यहाँ पे डेंसिटी सेम हो गई ना दोनों.
Absolutely. In this case, the density will always become equal. Okay. But if suppose it was a partial submergence ka case, something like this. If it was a partial submergence ka case, let's say exactly half of the solid was inside, then we would have had density of sphere into volume of sphere into gravity, into volume of sphere into gravity. This is mg basically. Okay, it is equals to upthrust. But when it comes to upthrust, it is sigma, which is density of water, density of liquid. Now, the amount of liquid that will be displaced, it is only this much. It is half of volume of sphere. It is half of volume of sphere. This is volume of liquid, people. I hope you have understood this.
Yes, sir.
Okay, into gravity.
Yes, sir.
So Gg gets cancelled, volume of sphere gets cancelled, and we have a relationship. The density of sphere will be equal to density of liquid by 2. We have a relationship here.
Yes, sir.
Now let's take the double liquid wala problem. So the question that I have found is something like, they have given us that oil is floating on mercury. There is mercury, Hg, and there is oil. Obviously, oil will float over mercury because mercury is solid, almost semi-solid, and oil is liquid, so it will float over mercury. However, there is a solid which is partially penetrated into the mercury and it is partially on oil, and now the system is in equilibrium. Very interesting. System is in equilibrium now. And they're asking us find the density of this solid. Density of solid. And they have given us some data. They have given us the density of oil is 0.8 gram per cc. Density of mercury is 13.6. That we know. 13.6 absolutely gram per cc. Okay. Chalo, let's do this. So again, what do we have? Mass into gravity. It is equals to upthrust. But the thing is, now upthrust is divided in two halves. One will be upthrust due to oil, another will be upthrust due to mercury. This is the only small trick. Mercury will have an upthrust like this, and oil will have an upthrust like this. That's it. Nothing else. Okay. So we have got two upthrusts. Mass is density into volume into gravity. Okay. Upthrust of oil, that's sigma of oil. Okay, sigma of oil, or then however you want to write, density of oil. What is the volume of oil? Half of sphere, don't you think? This is the volume of oil. Volume of the liquid displaced. This is the volume of the liquid displaced in the oil. Half, exactly half, people. Half of volume. Tell me if you have any questions, please, right now. Into gravity. People, upthrust is weight, weight is mass into gravity, mass is density into volume, density of oil is, okay, rho of oil, and volume of the liquid displaced will be half of the sphere. Similarly, we have got density of mercury. What is the volume of liquid displaced? Again, half. Again, half. Are you with me?
Yes, sir.
That's it. Vg gets cancelled. We have got rho is equals to density of oil by 2 plus density of mercury by 2. So this is basically arithmetic mean, people. Density of oil plus density of mercury by 2. And that is equals to 0.8 plus 13.6 by 2, which is 14.4 by 2. And that is 7.2. Let me check the answer. Absolutely correct. So small question, but interesting one. So I thought I will take this too in the class. So a very similar question I want you to do right now. I'm going to the next page. Okay. Here we go. So they have given us a cylinder this time, like this. Okay. The liquid of has density D above. The liquid has density 2D below, but it is not exactly symmetric. This much length is 3L by 4, and this much length is L by 4. That's it. And you need to find the density of the cylinder. Take your time. Because we did not take the mixture ka problem earlier in the class. So when I was setting basically good question papers, I came across these questions and I thought that maybe we should take these also. We'll get the answer in terms of small d.
Sir, 1.25.
Perfect. And in the chat box also, yes, perfect. Answer is 1.25 times small d, people.
Yes, sir.
3 students have got it. Should I do this, people? Chalo, let's do this quickly. So we have got a rho Vg will be equals to upthrust due to first plus upthrust due to second. Okay. Rho into volume of a cylinder, that's area into length. Okay. Into gravity. This is upthrust, that's mass into volume of the first, gravity. So not mass, density. Okay. M1 into gravity plus M2 into gravity. Okay. So rho, area into length, gravity. This is rho, density of the first liquid into volume of the first liquid, gravity, plus density of the second liquid, volume of the second liquid into gravity. Mass is density into volume now. Okay. So rho ALG, this is density of the first liquid is D, volume is area into what is length, 3L by 4. Length of the first liquid displaced, people, 3L by 4. Gravity. This is density of the second liquid is 2D. Okay. Volume of the second liquid displaced, that's area into length. Okay. Area cross-sectional area of all of them is same, but don't worry. Cross-sectional area of all of them is same, but the length of the second liquid this time is L by 4, people. Okay. Into gravity. So we have got AL gets cancelled, gravity gets cancelled, and we have got density is equal to 3D by 4 plus 2D by D is missing, 2D by 4, which is 5D by 4, and that's 1.25 times D. Absolutely correct. Okay. With this, we complete our classical mechanics revision here, unless you want me to take any specific topic again from classical. Anything else you want me to take from classical?